In this video, we're going to talk about the stability of radicals. Here we see a couple of things. First, we see that radicals tend to follow the same trend as carbocations. Tertiary radicals are more stable than secondary radicals, which are more stable than primary radicals, which are more stable than methyl radicals. Thus, we see that similar to carbocations, radicals are stabilized by two things, hyperconjugation and resonance. However, if we look at our chart above, the allylic radical is more stable than the tertiary radical, which means that resonance is the most important factor here. Now, what do I mean by hyperconjugation? Remember that hyperconjugation is the ability of nearby carbon and hydrogen bonds to donate in and stabilize a radical. So methyl radical, you can see here, is highly unstable because there's no nearby carbon-hydrogen bonds to donate into and support this p orbital. Let's remember the MO diagram for a carbocation has an empty p orbital here, and a nearby carbon-hydrogen bond can help donate in to stabilize that empty p orbital. Well, with a free radical, you've got one electron already in that p orbital. So when the nearby carbon-hydrogen bond donates in, we are actually putting an electron into an anti-bonding molecular orbital. So hopefully it's obvious why hyperconjugation is much more important for carbocation stability than it is for radical stability. This is also why resonance is much more important for radical stability than hyperconjugation. Let's take a look at some examples of resonance stabilizing radicals. Of course, we've said that allylic radical is the most stable of these types of radicals. So let's see how that would work. Here is an allylic radical, and the allylic radical can come in to form half of that pi bond there. This shows how we would draw a resonance structure for a allylic radical. The radical in red here joins with half of the pi bond in green to form the carbon-carbon pi bond on the right, and the other half of that left carbon-carbon pi bond becomes the blue radical. This bottom picture shows all the resonance structures of benzylic radical. Here's our benzylic radical, and you can see that that radical can get pushed up to a new carbon here, 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 and then it goes back to the original carbon as shown here, which makes benzylic radical a lot more stable than allylic radical, which only has one resonance structure. And I recommend that you walk through these resonance structures and make sure you feel comfortable drawing them out.